maybe, I don't know, a little boring, a little bit of a reminder of stuff that you guys should have learned in 151. I don't know, we'll see. We'll go ahead and get started to figure that out, okay? All right, so at the beginning of the semester, I had presented 3 questions that we were going to try to answer in this semester, okay? So the first question I had asked was, will a reaction occur? Will a reaction occur? Okay, the second question that I had asked is, how far will it go? So how far will it go? And then the third question I'd ask is, how quickly will it get there? How quickly will it get there? Okay, so ideally, you will see that we have answered 2 of these questions at this point in time, right? So with respect to how far a reaction will go, what is that kind of under the umbrella of, that topic that we have discussed thus far? How far will a reaction go? Equilibrium, right? So questioning how far a reaction will go, how many products versus reactants it'll have when it gets to equilibrium is dealing with the concept we have dealt with a lot this semester, okay? So that's question number 2. We've answered. It's done. What about question number 3? How quickly will it get there? How long does it take to get where it's going? What is that under the umbrella of? Topic that we have discussed this semester already. Kinetics, right? So remember, we started with kinetics. Kinetics was dealing with what? Rates of chemical reactions, right? That's going to tell us how quickly something will get there, okay? So ideally, we've answered 2/3 of the questions that we set out to answer this semester. Now we only have one more left, and that is, will a reaction occur, okay? That answer, or that question, is going to be answered with this chapter, which is going to deal with something called thermodynamics, okay? Okay, so let's start talking about thermodynamics. So long term, what we're going to come out of this chapter with is kind of an understanding about why chemical and physical processes happen at all, right? Why do we actually see ice melt? We don't really have an answer for that right now, right? We have a couple of laws that can help us understand various changes in energy, but we don't know why we see things always go from hot to cold and not vice versa, not the other way around, right? Why do gases expand to fill a container, right? Why do they expand as opposed to compress? Why is that a process that actually occurs, okay? And then if we want to get really philosophical with this, we could also say, what drives the universe in a forward motion? That's kind of what thermodynamics is trying to talk about. The answer to all of these questions, whether or not physical or chemical processes are going to occur, is going to come in the form of something called entropy. And this is not something that we have talked about yet, but you probably are familiar with it, having dealt with chemistry at some point in your life, okay? Kind of just a gross definition of what entropy is. Entropy has to do with disorder, the disorder of a system, or the randomization of a system, okay? In reality, though, and on a chemical and physical level, this has more to do with the spreading out or dispersion of energy. So we're going to spend a lot of time developing what entropy is. So before we get there, I want to remind you guys about a couple of things that you should have learned in 151, okay? But we'll come back to this concept of entropy. Okay, so thermodynamics is going to be really concerned, very heavily concerned, with whether or not something is called spontaneous or not, okay? So we're going to be questioning whether or not we consider a reaction or a chemical or physical process spontaneous. So what is a spontaneous process? So this is going to be something that is going to occur without any outside intervention, okay? So spontaneous processes happen, okay? We can also call these guys, instead of spontaneous, we can call these guys favorable processes. Okay, so if we have spontaneous processes, we will also have non-spontaneous processes. So non-spontaneous things are not going to occur on their own, but they still can occur. They just need outside intervention to actually get them to occur, okay? So long term, the idea for this entire chapter will be determining whether or not a chemical process is spontaneous or not, okay? What's really nice is to kind of try to compare this to a mechanical process, right? So for example, in mechanical systems dealing with physics, we can kind of understand whether or not something is going to be spontaneous, right? If we look at our little roller coaster on the top of this track, what is the spontaneous process that's going to occur at this point in time? It's going to fall to the bottom, right? So this is a mechanical system, right? It's dealing with all of the forces that are working on it and this mechanical idea, but we know what the spontaneous reaction for this will be. It will fall to the bottom of the track, okay? Now, does that mean that the reverse reaction couldn't occur? So if this guy goes to the bottom of the track spontaneously, does that mean that we couldn't take that cart and push it back up to the top? We can, right? But what do we need to put in? What do we need to supply? Energy, okay? So the reverse process is non-spontaneous, right? It doesn't just spontaneously go to the top of the little hill, but to get it there, we actually have to put in energy, okay? So spontaneous things are going to happen without any outside intervention. Non-spontaneous processes can only occur when you actually put outside intervention in. Okay, all right, so we're going to be concerned greatly with this idea of spontaneity in chemical reactions. Okay, so at this point in time, it's going to be important to note that there is a difference between spontaneity versus speed. Okay, so for example, there are two different allotropes of solid carbon. Okay, so one form of solid carbon you guys should be familiar with is diamond. Okay, so this is diamond, which is just nice solid carbon. Another allotrope of solid carbon is graphite. You are also familiar with this. Okay, this reaction, the spontaneous conversion between diamond and graphite, is spontaneous. I've just already said it, right? So spontaneously, diamond will convert into graphite, okay? Do you ever see this occur? Ever. If you have a diamond ring or a diamond earring or whatever, have you ever seen your diamond turn into graphite? No, right? So there's a difference between whether or not something is spontaneous, this is a spontaneous reaction, and how fast something is, right? So if we go back to something that we've already talked about, kinetics, right? This reaction, as is spontaneous, but is kinetically very inert. Okay, so what do you think I mean by inert? It's very slow kinetically, right? So we go back to this idea behind kinetics. What influences the speed or the kinetics of a chemical reaction? So if we go back to our little reaction coordinate diagram, which we probably should do, because we are coming upon a final at some point in time soon. And we drew out this idea, this progress of this reaction, right? So we can draw out reaction progress down below. And we can say that on the y-axis is some sort of energy, right? Let's say that we have our reactants, which are diamond. So carbon solid, this is diamond. And they're going to go to make products, carbon solid, this is graphite. Okay? Now, overall, it's spontaneous. I'm going to tell you that already. Now, where does kinetics come into this reaction progress? Where do I draw kinetics? So remember, there's something called what? That determined how quick or how slow a reaction was going to be. It had to do with energy. It had a little E to the A. Does anyone remember what E to the A was? Activation energy, right? So how does activation energy manifest itself on these little reaction coordinate diagrams? Right? What is it? What is it? What is the activation energy supposed to be representing? So if I drew it, it would be something like this, right? So this is the energy that has to be input to get a reaction to go in the first place, right? So what is the activation energy on this little diagram that I've drawn? It is the difference between the energy of what? What is this guy called up here? This was called the transition state, right? And so transition state was the unstable little thing. Once you got to the transition state, it would immediately fall to products. And where is activation energy? It's the difference between the transition state and the energy of the reactants, right? So this is the energy, this is the activation energy that you needed to put in to get a reaction to go in the first place, okay? Okay, so What was the relationship between activation energy and speed? The larger the activation energy, what could we say about the chemical reaction? Slower, right? And so, really large activation energies lead to very slow chemical processes, okay? So this is the difference between thermodynamics and kinetics, okay? Kinetics behind this reaction has a very large activation energy, so that's going to lead to an overall slow process. So within the length of our lifetime, you will never see graphite or diamond spontaneously convert to graphite because, again, the activation energy for this reaction is so large, so it is kinetically inert. It's never going to happen, okay? It is spontaneous, though, right? So if we wait the length of the universe and time, it will eventually occur one day, right? One more thing with respect to this. So again, kinetically really slow, but thermodynamically favorable. How can we speed this reaction up? We could add a catalyst, right? We could add heat, but it would be a lot of heat with respect to this reaction. A very good way, though, to speed a reaction up is to add a catalyst. Okay, just as a reminder with respect to kinetics. Okay, so that is the difference between spontaneity versus speed. Okay? Okay, so a couple other things that we need to talk about. We're going to go back to the concept of internal energy. Okay, so does anyone remember what internal energy was? We learned this in 151. So it's internal, right? It's inside something, I guess you could say. So the internal energy is defined as the sum of the kinetic and potential energies of the system. Okay? So what did we abbreviate, or what letter did we utilize to signify internal energy? Back in 151. There were two letters. There was an H. We haven't gotten to H, but there was also something else. E, right? So internal energy, we usually specify by the letter E, right? Okay, so as a reminder, internal energy, sum of kinetic and potential energies of the system, okay? So internal energy is something called a state function. Who remembers what a state function is? Nothing. No. Okay, so state functions. So what's the big idea behind state functions? So state function is something whose value only depends on the state of the system and not how it actually got to that state, okay? So this is going to be something whose value only depends on the final and the initial, so final and initial states of the system and not on the path that it actually took to get there, okay? So as kind of an example to explain what a state function is, I like to use this little altitude analogy, okay? So altitude, just like internal energy, is a state function, okay? Altitude. I don't think I'm spelling that right. Altitude. Nope, missing some T's. Altitude. Okay, so altitude is also a state function. Okay, so let's try to show what I mean by this state function. Okay, so if altitude is a state function, that also means that the change in altitude is also a state function. Okay, now what is change in? How do we normally measure that? Change in. How do we measure change in? Final minus what? Initial, okay? So when we measure this change in altitude, we're going to measure the final altitude minus the initial altitude, okay? So now let's imagine that we have a hiker. A hiker has just come to the mountain and they want to climb to the top of it, okay? So this hiker we will call hiker A, okay? Their initial altitude is 0 feet. And they decide, hey, I'm just going to hike all the way up this mountain. So hiker A hikes all the way up the mountain, gets to an altitude of 10,000 feet. Okay? This is hiker A, and this is the path that he takes. What is the change in altitude for hiker A? How would we calculate that? Change in altitude for hiker A, probably should use numbers. So what is the final altitude of hiker A? 10,000 feet, right? So 10,000 minus the initial altitude, very simple, 0, right? So overall, the change in altitude for hiker A is 10,000 feet. No big deal, right? Okay, now let's talk about hiker B. Poor hiker B. Doesn't get the nice, easy path that hiker A does, right? So this is hiker B, okay? So hiker B is going to start. Plan is to get to the top of the mountain as well, okay? Starts up the mountain, gets to about 3,000 feet, okay? Then something terrible happens. He dropped his water, okay? So he dropped his water back at about 1,000 feet, right? He's not going to be able to make it to the top of the mountain without his water, right? So he climbs back down to 1,000 feet, picks up his water. Okay, then once he has his water, he's like, okay, I can make it to the top of the mountain. Now I'm going to climb up to the top of the mountain. This was at 1,000 feet. Now let me do that again. So we're at 1,000 feet, climbs up to the top of the mountain. Okay, so 3 different little parts to the path that hiker B took. We're going to call this part 1. We're going to call this part 2. We're going to call this little part in section 3. What is the change in altitude for hiker B? So we can add up all the little bits and pieces to this path that he took, right? So if we want the overall change in altitude for hiker B, what is the first little path that he took? It went from 0 to 3,000 feet, right? So for that, final is 3,000 minus initial. Cover that, right? We're going to add to that the little section for number 2, the little yellow, right? So what is the change in altitude for that little yellow section? Final was 1,000. Oh, we shouldn't use yellow ever. Minus the initial, which was 3,000. Okay, and then we're going to add to that the final little chunk, which was little part 3, change in altitude 3. Okay, so in change in altitude 3, he went from 1,000 all the way up to 10,000. So final is 10,000 minus initial, which was 1,000. Overall, what is the change in altitude for hiker B? 10,000 feet, right? Doesn't matter, right? So overall, if we add these guys all together, change in altitude for hiker B is 3,000 plus a minus 2,000 plus a 9,000. Overall, it's the same exact 10,000 feet that hiker A hiked up, because change in altitude is a state function. It does not matter which path you take to get to your final state. All that matters is where you started and where you end up, okay? Internal energy is also a state function. Enthalpy is going to be a state function. Entropy, all of it is going to be a state function, okay? So long term, this is going to come back and be important for how we calculate all of these various values. Okay, so internal energy, state functions. What else did we learn in 151? We learned about a law of conservation of energy, right? So what does the law of conservation of energy tell us? What cannot be created nor destroyed? Energy, right? So energy, via the law of conservation of energy, can neither be created nor destroyed, okay? It can do other things, so it can change forms, right? So we can, what are the various forms? If we think of just mechanical systems, what are the various forms of energy? So for example, if I hold my little thing here and I hold it in the air, what does it have a lot of right now? Potential energy, right? So one form of energy is potential energy. If I drop it, what does that potential energy turn into? Kinetic, right? So now we also have kinetic energy, right? Kinetic energy is the energy associated with what? Movement, the motion of an object, okay? So when I have lots of potential energy, when I hold it up here, when I drop it, what does all that potential energy turn into? Kinetic energy, okay? So this is what I mean by changing form. So if we have potential energy, you drop it, it's all going to turn into kinetic energy. Still, energy is not created nor destroyed. Now, another thing that can happen is energy can be transferred, right? So let's say that we have some sort of billiard ball. Nice little billiard ball rolling along the table, and it's going to come into contact with another billiard ball, right? So this guy's rolling along, going super fast, has a lot of kinetic energy, right? What's going to happen when this little red billiard ball strikes the other billiard ball? Is it going to keep moving? Is this guy going to keep moving and the other thing's just going to stay the same, or what's going to happen? They're going to collide, and this guy is going to start moving, right? This guy is going to come to rest. What is that called? This one had lots of kinetic energy. It hit the non-moving ball. What did it do? Transferred its energy, right? How do we transfer energy? What did it do when it struck it? Force through a distance. What is that called? Work. Okay? So one way that we can transfer energy is in the form of work. What is another way that we can transfer energy? Let's say that we have my little coffee cup here. Lots of coffee. And it's steaming. It's very hot, right? And I put my hand to this very hot cup of coffee. So another way that we have energy, another type of energy, is thermal energy, right? So my coffee has lots of thermal energy. My hand, not so much thermal energy, right? It's kind of cold right now. Put my hand to that hot cup of coffee, what happens? Does my hand get colder and the coffee get hotter? No, my hand gets warm, right? It starts to gain thermal energy. How is that thermal energy being transferred to my poor little hand? Heat, the form of heat, okay? So another way that we can transfer energy is in the form of heat. And we give heat in chemistry the nice little letter Q, okay? All right, so again, law of conservation of energy. Can't destroy or create energy. That's great. It can change form, so we can have the changing between kinetic and potential, and it can also be transferred, right? And it can be transferred in the form of work or heat. Okay, so as a reminder, what was internal energy? Internal energy, our little E here, was the sum of both the kinetic and potential energies of the system, right? So internal energy can't change form. It has both of the kinetic and potential energies in it. If we have a change in internal energy, that can only come because something has been transferred, right? And there's only two ways to transfer, again, heat or work, okay? So when we have a change in internal energy, that is going to be due to the sum of the heat either absorbed or given off by the reaction or system and the work done on or by the system. Okay, reminders. All right, so with respect to these changing things, right, notice that in a couple of these I had thing that I was interested in. And then I judged what happened to that thing via everything that happened around it. What do we call the thing that we're interested in thermodynamics? We like to define things very specifically. So usually our chemical reaction or our billiard ball or our cup of coffee is what we define as the system. It's the thing that we're actually interested in studying, okay? So the system is the portion of the universe that we want to investigate. What is everything else? What do we call everything else? Surroundings, right? So surroundings is everything else. And most importantly, it's not just everything else, it's everything with the system can exchange energy with. So system has to be able to exchange energy with whatever the surroundings are. Okay, so a couple different types of systems. One type of system is what we call an open system. So in an open system, we can exchange both energy as well as mass with the surroundings. So both energy and mass can be exchanged with the surroundings. Second type of system is called a closed system, right? So in a closed system, we can exchange energy, but no mass. So matter cannot be exchanged with the surrounding in a closed system. Third type of system is isolated. Okay, an isolated system cannot exchange energy or mass. Okay, so considering these three types of systems, What type of system would a human being be? So humans would be open systems, right? Can we exchange energy? How so? We have heat, right? So we're cold, we're hot, we're whatever. So we're obviously exchanging energy that way. How else do we exchange energy? We consume stuff, right? So we absorb energy by eating things. What about mass? Can we exchange mass with the surroundings? Do we breathe? Do we eat? Do we get rid of waste? Yes. Okay, so humans are open systems. What would be a nice example of an isolated system? Isolated. Can't exchange mass or energy. A perfectly idealized isolated system. I close my little cap. What about this guy? What's the purpose of a hydro flask? Insulates things, right? It's trying to be this nice little vacuum jacketed thing so that what can't get out or what can't get in? Heat, right? Energy, okay? If we close it, ideally, matter can't get out, right? And so perfectly idealized hydro flask would be an isolated system. Can't exchange energy with the surroundings, cannot exchange matter either. Okay, all right. So we've defined our system, we've defined our surroundings. Together, what do the system and surroundings make up? This is kind of more a philosophical question. Together, what do they make up? The universe, right? So the system and the surroundings together make up the universe. Okay, so a couple more things with respect to reminders. There's 151. We also introduce you to the first law of thermodynamics. Right? So the first law of thermodynamics deals with energy. Okay? And what it states is that the energy content of the universe is constant. Why would that be? So number one, we have a law of conservation of mass. So we can't exchange or create or destroy. No. We have a law of conservation of energy. We can neither create nor destroy energy. What can we do with energy, though? We can change forms, right? So total content of the universe with respect to energy still going to be the same, no matter if it's potential or kinetic. What else can we do, though? We can change energy. How do we change energy? Delta E. So I have lots of kinetic. I punch this. What do I exchange my energy with? Or cold, hot. We can exchange energy. We can transfer it in the form of work and heat, right? So that's okay. We can exchange energy with other things. What about the universe, though? What is there for the universe to exchange energy with? Nothing, right? That's the whole point, okay? We can't create or destroy it. It's not going to matter if it changes forms. If we can't transfer it with anything, then the total energy content of the universe is constant. There's nothing with which it can be transferred to or from, okay? So that is the big idea behind the first law of thermodynamics. Energy of the universe is constant. Okay, all right. Now, let's get back to what we were trying to do in the first place, which was determine whether or not something was going to be a spontaneous process or not with respect to chemistry and chemical reactions. Okay, so again, if I draw out a nice little hill, so we've got a beautiful little hill, and we've got a beautiful little ball at the top of the hill, and we live in this mechanical world. If we look at this ball, and let's say it's being held down by something at this point in time, and we let this thing go, what's going to happen? What is the spontaneous process for this ball? It's going to fall down the mountain, okay? So in this mechanical universe, why is that? So at the top of the hill, what does this ball have a lot of? A lot of potential energy, right? As it goes down to the hill, it's going to settle in a valley, right? What does it have? Not very much of at this point in time. Potential energy, right? So it goes from the region with a very high potential energy to a region with a very low potential energy. Okay, so that's great because mechanical systems always tend towards lowest potential energy. So we can utilize that fact to kind of predict spontaneous processes in mechanical systems. We know it's going to fall down the hill because that has a lower potential energy state. It would be ideal if we had something very similar for chemistry, right? If we looked at some sort of chemical reaction, we said, oh, well, the products of this reaction have a lower chemical potential energy than the reactants do. So we know that this reaction is going to occur, okay? That's the ideal. That's what we're trying to work for, is this chemical potential energy. We don't have it yet, okay? We do have a couple of things that are going to help get us to this chemical potential energy. The first thing that we're going to talk about is, again, something that we've talked about before, this concept of enthalpy. So what was enthalpy? Enthalpy. Something about heat, maybe? Right? So enthalpy, with respect to chemical processes, right? We talked about enthalpy in, again, 151. So what little letter do we utilize to signify enthalpy? Q-ish, but we give it a different letter. It's its own little thermodynamic function. So enthalpy gets the letter H. Okay, so H is what enthalpy is represented by. So we have this really drawn out definition of enthalpy. So enthalpy technically is defined as the sum of the internal energy plus pressure times volume. That doesn't matter though. So things happen, math happens, and at the end of the day, we can define the change in enthalpy in a chemical reaction as what? What is Q? Heat, right? So enthalpy, change in enthalpy, is also referred to as the heat of reaction. And most importantly, this little lowercase p, what do you think this little lowercase p represents? In terms of like gases and stuff, what does p represent usually? Pressure, right? So enthalpy is, again, the heat of reaction at constant pressure. Okay. Do I need to mention that? Yeah, I'll mention it in a second. Okay, so that's enthalpy, great. Heat of reaction at constant pressure. So now, we talked about enthalpy for quite a bit of time with respect to 151. There were two different types of reactions depending on the enthalpy change in a reaction, right? So what was one of them? Endothermic versus exothermic, right? So if we had, let's say, a reaction that was what we call exothermic, that meant that if we drew out a nice little reaction coordinate diagram, we label H on the Y, and we say, here's our reactants, and here's our products, okay? And so again, delta H is going to be H final minus H initial. If our products are at a lower energy state for something like this, what's going to be my overall sign of delta H? It's going to be negative, right? Because my products are at a lower or smaller amount of enthalpy than my reactants, right? So this delta H was going to be negative, and we called those exothermic reactions, right? And again, this is with respect to our system, okay? So this difference in energy here, this difference in enthalpy, where is that going to go? If this is my system, and my reactants are higher enthalpy than my products, where is that difference between them going to go? To the surroundings, right? To whatever the system can exchange energy with, okay? So that means, are the surroundings going to gain energy or gain heat, or are they going to lose it? They're going to gain it, right? What is that going to do overall to the temperature of them? Because heat is directly proportional to temperature, right? So if my surroundings are gaining heat, what's that going to do to the temperature? It's going to increase them, right? So a big distinguisher with respect to exothermic reactions, we had a negative delta H, and that difference, that loss of enthalpy, went to the surroundings. That ended up increasing the temperature of the surroundings. And then I just write all over everything. Okay, so that's exothermic, right? Good proxy. You look at your system, Look at your surroundings, what happens to the temperature, okay? What was the other type of reaction that we had with respect to enthalpy? We had exothermic reactions. What else do we have? Endothermic, right? So endothermic reactions, we had a delta H that was positive, right? That's because our reactants were at a lower enthalpy state than our products, right? So final minus initial, products minus reactants is going to give us a positive value. What happened overall? How did these reactants get to these products? What did they need to take in? Heat, right? And so if the reaction is taking in heat, where is it coming from? The surroundings, right? What's happening to the temperature of the surroundings? They're getting colder, okay? So for endothermic reactions, heat is being absorbed by the reaction, by our system, and the temperature of the surroundings are getting colder. Okay. All right, so just a reminder, that's what enthalpy was, right? So again, going back to this ideal of making or determining this chemical potential energy, right? Where we have this state where we can look at this thing, whatever this thing is, this chemical potential energy, and we can say, oh, well, all systems are going to tend towards lowest chemical potential energy. So we could propose maybe that enthalpy would be this thing, right? So then if enthalpy is our chemical potential energy, and we're always wanting things to tend towards lowest enthalpy, then what type of reactions would be spontaneous? Exothermic reactions or endothermic reactions? Exothermic reactions, right? So if enthalpy was our chemical potential, then exothermic reactions, all of them would be spontaneous processes, okay? So now, can you think of any reactions that are endothermic and are spontaneous? So think about that. I'm going to propose to you 3 separate reactions, and I want you to tell me whether or not they are exothermic or endothermic. Don't say it out loud, just think about it. So 3 different processes. I have the melting of ice, I have the evaporation of sweat, and I have the dissolving of NaCl in water. So are these processes exothermic or are they endothermic? Think about it for a second. I'll regroup. Okay, so melting of ice. Is this exothermic or endothermic? Endothermic. How do you know this is endothermic? So if the ice is our system, what's the surroundings? Ice is a system. What is it in? Whatever it's in, right? Water. Let's say it's water, okay? What's happening to the temperature of the water? It's getting colder. Okay, so that's a big indicator that this is endothermic. The process of ice melting is absorbing water from the surroundings, which are the water that surrounds it. So the temperature of the water gets colder. What about evaporation of sweat from skin? Is this exo or endo? Competing ideas here, right? So the sweat is the system. That's important to note, right? So the sweat evaporates. What happens to the surroundings? What is the surroundings in this case? The skin, right? What happens to the temperature of your skin when your sweat evaporates? Cools down. All right, so is it exothermic or endothermic? If the sweat is the system and your skin is the surroundings. What happened with ice? The ice surroundings got cooler. It was endothermic. Surroundings get cooler. It's endothermic. So endo, again, and then the dissolving of NaCl in water. Who knows about this one? Has anyone sat there and dissolved a bunch of salt in water and felt its temperature? it again gets much, much, much colder, right? So this is also an endothermic process, okay? All right, so we get to this point, all of these are endothermic. Are they spontaneous? Do they happen without any outside intervention? Yes, right, they happen. If I sweat, I'm sweating right now, it happens, right? Salt, if you put it in water, yes, you have to stir it, but if you just left it there, it would still dissolve, right? Ice melts, they melt, right? So these are all spontaneous processes. They're all endothermic, unfortunately. So because of that, guess who's not going to be our chemical potential energy? Enthalpy is not going to be our chemical potential energy, right? If it was, then all exothermic processes would be spontaneous, all endothermic processes would be non-spontaneous. We have just identified 3 things that are spontaneous and endothermic, okay? So unfortunately, enthalpy is not our chemical potential. I should note, though, that most exothermic reactions are still spontaneous, okay? So we'll find later on that most things that are exothermic are spontaneous overall. Okay, all right. Build this up to get to this point to tell you, oh, no, it's not enthalpy. So what is it going to be? Where are we going to get this chemical potential energy? So if we look at these things that are endothermic and yet still spontaneous, we should ideally sense some sort of trend, okay? So if we look at melting of ice, okay, so melting of ice, endothermic process, but it's spontaneous. What's happening in this process to the freedom of motion of these molecules? Right, so if we compare the solid water and our ice, how much freedom of motion or freedom of movement do you think solid water molecules have? Can they move very much if they're in this little packed solid? No, right? So solid water does not have a lot of freedom of motion. So again, this is our ice. What happens to their freedom of motion when they move into the liquid state? It should increase, right? So liquids can move relative to one another, right? So now they're not just stuck in this big crystalline lattice. Now they can move relative to one another. So going from solid to liquid water, we're going to increase freedom of motion. So we can kind of understand this increased freedom of motion, increased freedom of movement in terms of this concept that we introduced earlier called entropy, okay? So overall, this increase in freedom of motion is going to increase randomization of our system. It's going to increase what we call disorder, and again, it'll increase entropy. Same thing with respect to evaporation of sweat, right? So evaporation of sweat, what are we looking at? We're looking at liquid water going to what? Gaseous water, right? So again, in that process of going from a liquid, where we do have some freedom of motion, right? These guys can move relative to one another, to a gas state, how much freedom of motion do molecules have in the gas state? Lots, right? They can move everywhere comparatively to one another. Okay, so again, this is an endothermic process where we see this increase in freedom of motion, this increase in randomization, this increase in entropy. Okay, so long term, big idea behind this comes into this increase in disorder and this increase in entropy. Oh God, I don't know if I have this in me. Okay, so entropy is not just this idea behind disorder, right? There's actually a statistical quantification, a statistical definition for it, okay? And what it is given as is this. So entropy is a thermodynamic function that increases with the number of energetically equivalent ways to arrange the components of a system. So that makes very little sense, and I'm positive of that, okay? But it is essentially quantified in this equation. And I'm going to explain what everything in this equation means, okay, to try to get at the real statistical idea behind entropy. Not just thinking, oh, it's more disorder and it's more randomization. So one thing to note, we give entropy the handy little letter S, okay? So enthalpy was given H, entropy is given S. So, increases with the number of energetically equivalent ways to arrange the components of a system. So this is our little entropy here. It is given by K K is a constant. It's called Boltzmann's constant. We're not going to really worry ourselves with respect to K at this point in time. Just note it's a constant. Then we have this little thing here, ln of W. But what is W? No one knows, I know. W is what we mean by this energetically equivalent ways to arrange the components of a system. So I'm going to demonstrate to you what W really means in terms of systems, etc. Okay? To do so, we're going to get back to the idea behind an ideal gas. Okay? So, what is W? That's what I'm trying to explain. Let's imagine that we have an ideal gas. Okay? We have this nice little ideal gas, and it has a certain amount of energy. Okay? So this ideal gas, we'll draw a little picture of it. It's contained in this beautiful little beaker, which is capped, it's sealed, so it can't get out. And there are, let's say there are 4 molecules of this gas in this beaker. Okay, so the total amount of energy for an ideal gas is given by the pressure of the gas, it's given by the volume of the gas, and it's given by the temperature of a gas, okay? So this pressure, not yellow, this pressure, this volume, and this temperature tell us overall that the energy of this ideal gas is 10 joules, okay? So these conditions define what we call the macro state of the system, okay? So overall, this macro state, total energy of our little ideal gas is 10 joules. So now when we peak down into our gas, we have our macro state, which is again defined by the conditions of the system. Does that mean that every little gas particle in our system has the same energy? So we go back to the idea behind gases. Remember, with respect to kinetic energy and velocities of gases, there was always a distribution, right? There's always some sort of little bell curve, right? And so at any given point in time, let's say that we take a picture of this gas, okay? We take a picture and we find that the red guy has about 2 joules of energy, and the blue guy has about 3 joules of energy, and the green guy has about 1 joule of energy. So how much is left for the little yellow guy to have? 4 joules of energy, right? So again, all of them are going to sum up to the total energy of the macro state, okay? This little distribution of energies in our system is what we call a microstate. This is a microstate of the system, okay? So as things progress, what's happening with respect to these gas molecules? We'll say that we took this picture at 0 seconds, okay? Are the gas molecules stationary? No. What are they doing? They're constantly moving, right? What's happening when they constantly move? Are they colliding with one another? If we consider this going back to just little billiard balls, when they collide, what's happening between them? They're transferring energy, right? So we come back 10 seconds later, and we take another picture. And in our second picture, now red has 3 joules, and yellow has 1 joule, and green has 3 joules. And then what is blue going to have? 3 more. Okay, 3 joules. Okay? Again, same total energy of the system, same total macro state. This is another microstate of the system. Okay? So now, there are 1,000 different ways that we could arrange the energy in this system, right? What these individual microstates are trying to represent is what W is in the entropy equation, right? It is the what number of energetically equivalent ways to arrange the components of a system to achieve a particular macro state, right? So again, microstates, all of them summed together is what W is, right? How many different ways can we arrange the components of the system to achieve our overall macro state? Okay, that's what W is. Okay, and I think I'm going to end there for tonight because I can't. We'll start by indicating what W is going to tell us about entropy next time. I think. Oh, man. So yeah, the exam. Okay, so the averages were not super great. It was about a 60-ish, I think, 64. So because of that, I'm going to offer an opportunity for extra credit next week, next Thursday, at the end of class. I'm going to give you guys a quiz, okay? And I'll tell you what the quiz is. It's going to be a titration of a weak acid with a strong base. The exact same way that I did it here, right? The quiz is only going to be worth 15 points, so note that, but it's 15 points of extra credit. You do not have to take the quiz if you don't want to, if you're happy with your grade, but if you would like to stay and take the quiz next Thursday, it will be another titration, just like I presented, and the last problem in this exam. Okay, that's it. So let's see you in the lab. I have the key up here, if you want to look at that, and I also have your exam scores. So if you want to come up and get them, I know they're not moving around.
I think it's like the teacher. I think it's like whatever. Charles. He was awesome.
I don't know if it's first name or last name B.
Wait, what? What is the last name?
Victor.
B. I know.
Always the last
Sometimes,
one.
like literally, sometimes I like look at people like I know their name.
I know
I
it,
don't
but
know their name. I don't know what happened. Then I remember the ones that changed their name.
There he is.
Thank you.
G comes after. No, comes before. Started. So, a couple reminders. Sapling, KSP homework, do the homework. I've also opened up the thermodynamics homework, so you guys should be able to work on that. I don't think that has a due date as of yet, but it probably won't be for a week or so. So, try to get to that, looking at those questions as early as possible. Also, because of the exam grades, we're going to have the extra credit quiz. That's going to be next week. Okay, so next Thursday, at the end of class, I'll give you guys about 20 to 25 minutes to take the extra credit quiz. Again, that is going to be another titration problem. Okay, so exactly the way I presented it on exam number 2, you can guarantee it's probably going to be the exact same. Okay, so know how to do those titration problems. And you should be able to earn all of the 15 points of extra credit. Okay? If you have questions about those titration problems, I have videos online that essentially everything that I did in class, I posted online. Also, you can ask me if you want me to help explain something. I can do that after class as well, okay? Okay, so we're going to continue on with entropy, which is where we got to last class. So we had defined what entropy was, right? So entropy is a thermodynamic function, and it is given by this little equation called the Boltzmann equation, right? So entropy, we give the little letter S, right? This is equal to KB, which is just a constant. We don't have to really worry about that. ln, natural logarithm of W, okay? And the big concept behind entropy comes in the form of W, right? So W was the energetically equivalent ways to arrange the components of a system, right? And so I tried to explain W in terms of macrostates and then all of the various microstates that could make up a macrostate. That is the concept of W, okay? So as we had found, ideally, or hopefully one day we'll find, as W increases, so as the number of ways that we can arrange the components of a system increase, entropy is going to increase, okay? So as W increases, entropy will also increase, okay? All right, so now we're going to kind of apply this again. So I kind of tried to demonstrate it with respect to my little container of an ideal gas and how the various ways we could have arranged the microstates to make up the macrostate. I'm going to do that again, okay? But I'm going to take that down just a little notch. So now instead of 4 molecules in this empty vessel, we're just going to be looking at 2 molecules, okay? And we're going to be comparing 2 separate systems. So we're going to compare system A to system B in terms of the W's and how that affects the overall entropy of the systems, okay? Okay, so the macrostate for both of these systems is going to be 4 joules total energy, okay? So both of these systems have the exact same macrostate, and this is total energy of 4 joules, okay? Now, the only way these systems differ is the number of energy levels that these little molecules can access, right? So for system A, there is only one energy level. It is 2 joules, right? System B, on the other hand, has 2 energy levels. It has a 3 joule and a 1 joule, okay? Again, what are the molecules, what are their total energy sum to in both of these systems? 4 joules. That is the macrostate, okay? Now, if we consider system A, how many different ways could we arrange these 2 molecules to obtain that overall macrostate, that 4 joule macrostate? Is there any way that we can arrange this besides the way it's already being arranged right now? No, right? So the only way that we can arrange these 2 molecules, because we only have 1 energy level, is the way that we are showing on the screen. And so W, the number of microstates for this, would be 1, okay? Okay, so now let's consider system B, right? So right now, as is in system B, we have the red ball and the 3 joule energy level. We have the blue ball and the 1 joule energy level, right? Total energy is still 4 joules. So they arrange themselves. Oh, God. Oh, Jesus. Oh, no. Okay. Hopefully I didn't break it. Okay, so 4 joules, total energy. All right, so are there any other ways that we could arrange these molecules to obtain our overall same macrostate of 4 joules? So right now, red is in 3, blue is in 1. Could we do this a different way? Yes, right? So we could switch them, okay? So blue could be in 3 joules and red could be in 1, right? So for this system, how many microstates are there? How many different ways can we arrange this to get our overall macrostate? 2, right? So for this system, W is 2, right? So which system has the most entropy? System B, right? Because W is 2, that's going to give S overall a larger value than W being equal to 1, which S would be 0, okay? So system B, because of that, has more entropy, okay? Now, there's an important little point to note here. With system A, we only had 1 energy level, right? That's the only thing that these little molecules could access. System B, though, how many different energy levels were there? 2, Okay, so we can also consider entropy, instead of just considering microstates and macrostates, we can also consider it as a dispersion of energy. The more energy levels that we give to a system, the more ways it can disperse energy within that system. Okay, so entropy is also going to increase with the number or the amount of energy that we can disperse in a system. Okay, it's kind of a good measure of just overall dispersion of energy. Okay? Okay, so now this is going to lead us, because the whole purpose of all of this was how can we know whether something is going to be spontaneous or not? So this is going to lead us into our criteria for spontaneity with respect to chemical and physical processes, which is called the second law of thermodynamics. Okay, so the second law of thermodynamics states that for any spontaneous process, the entropy of the universe must increase. Right? So delta S of the universe must be positive, right? Must be a positive value. So how do we normally measure delta S, or delta anything? So delta S, we'll say the universe, is going to be the entropy of the final state, right? So S final minus S initial. Okay, so if this has to be positive, if we have a spontaneous or favorable process, what does that tell you about the entropy of the final state versus the entropy of the initial state? Final always has to be greater, right? So another way that you can formulate the second law of thermodynamics is that entropy is tending towards a maximum value, right? So entropy is tending towards a maximum. Okay? Now let's compare this with the first law. What did the first law state? The first law of thermodynamics. It talked about energy content. What did it tell us about the energy content of the universe? It's constant, right? So the first law of thermodynamics tells us that the energy content of the universe is constant. The second law of thermodynamics tells us that entropy is tending towards a maximum value. Okay, so these are big, gigantic laws with respect to our little thermodynamics. Okay, so if we want something to be spontaneous, the final state, the final entropy state has to be bigger than the initial entropy state. That change in entropy for the universe has to be a positive value. Okay, just as a little reminder here, entropy, just like enthalpy, is a state function, right? So remember, state functions don't depend on the path that you take to get to whatever state you're going to. All they depend on is the final and the initial state of the system. Okay, so entropy is just like that as well. Okay, so I know we're going to go back to a nice little illustration of this idea, but we're going to show you how entropy, and this idea of entropy tending towards a maximum value, is going to allow you to predict the final outcome of a process, the final spontaneous outcome of a process. Okay? And I'm again going to use a nice little idealized system with very few molecules in it to try to illustrate this point. Okay? So let's consider our little flask here. Okay? Our flask at the left has 4 little molecules in it. Okay? Our flask at the right has nothing. Right now, this flask is sealed from the right flask via this little stopcock. Okay? If we consider the entropy of this system right now, how many different ways can we arrange the components of this system to achieve this state? Are there any other ways that we could actually arrange these components? No, right? So they're all in this left flask. There's no other way that we can arrange it. So right now we're going to say that our entropy initial is going to be KB ln, that's an ugly ln, ln of W, and W for this state is just 1. So KB ln of 1, what is entropy here? It's just 0, okay? So this is our initial entropy value. Now, we're going to open up the stopcock, okay? You could probably predict what's going to happen, just intuitively. If I open up the stopcock, what's going to happen? What is going to be the final state of the system, do you think? Just proposing it. Equal numbers, right? We're going to end up with 2 in one and 2 in the other, right? Because what happens, what do we know happens with respect to gases? They diffuse to fill their container, okay? We know that's a spontaneous process, but I'm going to show you why why that actually occurs, okay? Now we're going to consider 3 possible outcomes to this system once we open up the stopcock. The first outcome we're going to call state A, and we're going to have all of the molecules stay in the left side of the flask, right? So in state A, everyone stays over here, okay? Another possible outcome is all of the molecules move to the right, right? So all of the molecules go over to the right side of the flask. We'll call this state B. The third possible outcome, we're going to have 2 in one and 2 in the other, okay? Is there another possible outcome to this that I'm not considering? Right, we could have also had a 3 and then a 1, as well as a 3 and then a 1, but we're just going to excuse that right now just to not get super into the weeds, okay? So 3 possible outcomes. All of them stay in one, all of them go to the other, or we end up with 2 and 2, okay? Now, when we're considering the number of W's for these 3 possible states, if we consider state A, right, how many different ways could we arrange the components of state A to achieve that state A? Just one, right? All of the molecules stay there. So there's only one way that we could arrange state A to actually get there. So W for this guy would still be 1, okay? What about state B? So everyone moves over, right? So everyone moves over to the right side. What are the various ways that we could arrange this to achieve this overall state? Just one, right? There's only one way. They all go there. They're all in that flask, okay? So W, again, would be 1 for this situation, okay? Now, state C. How many possible ways could we arrange this system so that we have 2 in one and 2 in the other? So we could go through that, right? We could go through all the various permutations if we labeled all of our little molecules. So we have, let's say this is 1 and 2, and this is 3 and 4. So one of the outcomes that would give us 2 and 2 is we could have 1 and 2 in one, 3 and 4 in the other. We could have 2 and 3 in one, 1 and 4 in the other, etc., 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 so on. We go through all of those possible ways, right? The number of possible ways that would give us the 2 and 2 ends up being 6. Okay, so there's 6 possible ways that we could arrange this to get the outcome that we want, this macro state, okay? So W here is going to be equal to 6, okay? Now, if we ignore entropy, and ignore the fact that entropy has to be positive for a spontaneous process, what about statistics? Because that's really where entropy comes in at. Who is the statistical favorite outcome for this? There are 6 possible ways that we could get this outcome, right? What about the outcome where they all stay in one? How many possible ways could you achieve that outcome? Just 1, right? How about everyone moving to the other side of the flask? There's only 1 possible way you could achieve that outcome. You get 6 possible ways, so because of that, the probability of finding this state is 6 times more probable than finding them all in one or all in the other, okay? Now, that doesn't seem like that big of a deal. 1 in 6, right? You could probably find all in one and all in the other, but as we increase the number of molecules that we put in here, that probability is going to increase gigantically, all right? So if we considered, instead of 4 molecules, if we considered 10 molecules, how many possible ways, you don't have to know this, how many possible ways do you think that we could arrange 10 molecules so that we end up with 5 in one and 5 in the other? Very large number, starts to go up, so with 6 for only 4 molecules, for 10 molecules, this ends up being 252 possible arrangements. That would give us 5 in one and 5 in the other. What about for 20 molecules? So 20 molecules, how much do you think that's going to increase by? Where you get 10 in one and 10 in the other. So this ends up being 180,000 possible ways that you could arrange 20 molecules that you end up with 10 in one and 10 in the other. Okay? Now again, on the terms of chemistry and everything that we deal with, do we deal with 4 molecules? No. Do we do 10? No. Do we do 20? No, right? If you thought of a mole of molecules and all the possible ways that you could arrange the components so you end up with half of the molecules over here and half of the molecules over here, it would be a gigantic probability of that, you finding that state at the very end, okay? So there is obviously an energy consideration with respect to entropy, but entropy is also very statistical in nature. The reason why we see gases diffuse to essentially fill their container is because that is the statistical most probable outcome for that solution, okay? Okay, so again, if we want something to be spontaneous, it has to have a positive value for entropy, okay? And we're always measuring entropy in terms of the final state minus the initial. If delta S is positive, if we have a spontaneous process, then final entropy has to be greater than initial entropy. Okay, so let's try that in terms of a little conceptual connection question, okay? I have 3 different flasks. I have flask A, I have flask B, and I have flask C, okay? This is our initial state for each flask, and this is our final state for each flask. I want to know which of these has a positive delta S. Go ahead and try this. Oops. Oh, still going. Okay, so most of you did pretty well on this one. Got a 69% approval rating, good rating. So the correct answer here for a positive delta S would be A. All right, so in A, we have things that are semi-condensed that essentially diffuse out to fill their container. You don't even really have to think of this in terms of W's. You can try to if you want. But again, spontaneous processes are going to have a positive delta S, right? And so because of that, these guys going to fill their container gives us the positive delta S. What happens in B? We have things that are spread out. What do? They recondense, right? Is that a spontaneous process? Have you ever seen that occur? No, okay? So same kind of thing happens in C, so make note of that. Okay, so that's enough about W, okay? So we don't have to go back to W. We're not going to calculate W's anymore. But we kind of need to have this concept of W so that we can understand how we can predict entropy changes as we're actually going about our physical and chemical processes, okay? So we had talked earlier about spontaneous processes and there being this great dependence on the degrees of freedom by which our process was essentially obtaining, right? So when we had looked in going from a solid to a liquid to a gas, what had we been doing in going from solid to liquid to gas? We gave the molecules more freedom of motion, okay? So more freedom of motion, or more degrees of freedom molecules have overall, the more microstates that are accessible to them, okay? So more degrees of freedom, more freedom of motion, more W, more microstates. Also, more ways that they can disperse energy within their system, okay? So what is that going to mean in terms of entropy? Is as we go from a solid to a liquid to a gas, so solid to a liquid to a gas, we're getting more W's in that process. What's happening to entropy overall? We're increasing entropy, right? So we're going to see an increase in entropy as we move between these state changes, going from solid to liquid to gas. And again, it's because we're giving more molecular motion, more degrees of freedom, greater dispersion of energy within the system. So we increase S. Okay, so you may say, well, how do molecules actually disperse energy within themselves? So we're giving them more degrees of freedom, but how do they actually, what do they do with those degrees of freedom? So there's a couple of different ways that molecules actually disperse energy within themselves, and it comes about in their molecular motion, okay? So there are a couple of different types of molecular motions. The first one that we talk about is something called translational motion. So all translational motion is like straight line movement, right? It's essentially movement in three-dimensional space. It would take something like, let's say, an argon molecule. So something like argon's just floating around, hitting walls, etc. That's what translational motion is essentially referencing, just three-dimensional straight line motion. There are also vibrational motions. So all molecules that have bonds actually vibrate. The bonds themselves vibrate. They act like they're little masses on a spring. They also move relative to one another. So there's also vibrational motion. And then there's also rotational motion. So molecules will actually rotate like little tops being spun on their heads. Okay? So lots of different ways that molecules can essentially disperse this energy within themselves, okay? It's important to note, number one, more atoms, more degrees of freedom, more microstates, more molecular motion. Also, more bonds, more motion, more degrees of freedom, more ways to disperse energy within themselves. Okay, so now a couple of other things that are going to affect the entropy, right? So number one, if we increase the temperature, what are we doing? If we increase temperature, what are we adding to a system? So we're adding thermal energy, right? Temperature is a measure of thermal energy. So if we increase the temperature, we're essentially adding energy to a system. So if we add energy, there's going to be more ways to disperse that energy. Okay, so as we increase temperature, we tend to increase entropy as well. As we decrease temperature, we're going to decrease entropy. Also, volume is another important thing. So as we increase the volume, so we have like a sample of gas, we increase the overall volume. What's that going to do to degrees of freedom or degrees of motion or freedom of motion? Okay, they're going to have more freedom of motion, they're going to have less freedom of motion if we increase the volume. More, right? So if we increase volume, that also tends to lead to an increase in entropy. And then if we increase the number of independently moving molecules, we will also increase the entropy, okay? So overall, what does this mean? This means that we will have a spontaneous process or a positive delta S when we go from a solid to a liquid, when we go from a solid to a gas, a liquid to a gas, less gas molecules to more gas molecules, or if we increase the temperature or volume of a container. Okay, so lots of different ways that we could see overall delta S being positive. Okay, so now let's try that. So I want you guys to utilize these great principles to predict whether or not the following processes are spontaneous or not, whether they have a positive delta S. So actually I'm asking just for the sign of delta S. So the answers here will be positive or negative. What? It goes from a gas to or it goes from a solid to a gas. Okay, so go ahead and talk about these. So most of you guys did really good on this. So in going from a gas to a liquid, what's going to happen with respect to molecular motion, with respect to degrees of freedom? We're going to decrease, right? So what's that going to do to entropy? It's also going to decrease. So delta S here would be negative. Okay, so the trick was knowing what solid carbon dioxide subliming means. So that's going from a solid to a gas. This is just dry ice, right? What is the process of moving from a solid to a gas without passing a liquid? So we're gaining much more degrees of freedom, much more molecular motion. So we have a positive value here. And then the last one is not trying to be super tricky. We have a gas and we have gases. What's going to be the deciding factor in determining if this is a positive or negative delta S? More molecules, right? So the more moles of gas that are produced, the more entropy, right? So we have 2 molecules going to 3. So because our final state has more molecules of gas, this is also going to have a delta S that is positive, okay? Okay, so a couple more things, and then I'll give you the activity. We have been qualitatively determining overall delta S's for these physical processes, just knowing that, gases have more degrees of freedom, more entropy than liquids, than solids. We're going to want to actually calculate these values, okay? And so before we can actually calculate these change in entropy values for a given chemical reaction, we have to define a couple more things, okay? So I just want to remind you guys, from 151, we dealt with changes in enthalpy. Right? And so we gave you an equation at the end of 151 or wherever it was that allowed you to calculate the enthalpy of any reaction giving those tabulated standard lists of enthalpies of formation, right? So we could calculate this guy from these tabulated lists of enthalpies of formation, okay? Now, enthalpy is a relative thing, right? All we really care about with respect to enthalpy is the fact that we're calculating a change in enthalpy, okay? So because of that, we kind of defined a relative 0 for all of this, right? So we had defined things that had an enthalpy of formation of 0 as what? Who had enthalpies of formation that were 0? Anything in its elemental form, right? So any molecule or any compound in its elemental form, we defined as having a enthalpy of formation of 0. That was a relative thing. That is something that chemists did to make life easier, okay? We're going to do the same type of thing with respect to entropies, right? We're going to want to calculate these entropies of reaction, and we're going to do that from tabulated standard lists. The only thing that's different here, though, is that entropy is absolute, right? There are no relative values. We have a 0 of entropy, and we measure everything relative to it, okay? This is going to bring us to the third law of thermodynamics, which tells us what this entropy of 0 is, okay? The third law of thermodynamics states that for a perfect crystal at absolute 0 Kelvin, we will have an entropy value equal to 0, okay? The idea behind this is there is only one way to arrange the components of that system, so this is the state where we have entropy equal to 0, okay? Everything else relative to that, what do you think is going to happen with respect to entropy values? You think they're going to be positive or negative? Positive, right? So everything else is going to have a positive value for entropy because everything's going to have more W's, more ways to arrange it comparatively to our perfect crystal, okay? Okay, so how are we going to use that? So again, as a reminder, when I talked about these enthalpies of formation, what did this little 0, what did this little knot up top mean? What did it indicate about what we were doing with the reaction? Or what state the reaction was at? So this little guy told us something about the reactants and the products, right? And what it told us is that we were at standard state, right? So we have a defined chemical standard state. That standard state is given by the following sets of conditions. So if you are a gas, you have exactly 1 atmosphere pressure, right? If you are a solid or liquid, you're going to be the most stable form of that solid or liquid. And then if you are in solution, your concentration is 1 molar, okay? The whole idea behind this, we're telling you that these are the enthalpy values when all of the reactants and products are at standard state. Okay, so we're going to do the same exact thing for entropies, okay? So for S, except we're not going to have a delta in front of S anymore, okay? We get rid of the delta because, again, entropy is absolute. We're going to be calculating these things from these standard tables, right? So these are telling you that all of our reactants and products are under standard state, and these are where these values come from. Okay, so entropy, just like enthalpy, is an extensive process or property. What does extensive mean? So intensive was unique to the thing, right? But extensive depended on what? The amount of something that is there, okay? So depending on how much of whatever we're looking at is there is going to depend on the overall entropy value. Okay, all right. So then, now that we have defined those little reminders, standard state, etc., how are we going to calculate these entropies of reactions? So we're going to be utilizing these beautiful little tables just like this, right? These are our tabulated standard molar entropies, okay? This is kind of where we start to get into looking into the appendix, because all of these lists, all of these tabulated standard molar entropies are usually in the appendix, okay? So we're going to find this for this chapter. As we move on to the electrochemistry chapter, we will also be dealing with things in the appendix. Okay, so I just want to talk about a couple of trends, right, that actually don't have to go back to the appendix or anything, that we can just kind of get a relative idea about, just understanding a couple of different properties with respect to entropy, okay? So the first little trend that we're going to look at is what happens to entropy as we increase molar mass. So if we looked at the noble gases, for example, as we go from helium all the way to xenon, what's happening to the molar mass of the gas? So we go from top to bottom, what happens to molar mass, our size? Increases, right? What do we see happen to the entropy values of these guys as we go from top to bottom? Increases as well, okay? So just if molar mass increases, the larger the thing tends to be the more entropy the thing has, okay? All right, so that's molar mass. What about different allotropes? So again, an allotrope is just a different form of whatever physical state you're looking at. So for example, there are 2 allotropes for carbon, diamond and graphite. What we find with respect to these trends in entropies is the less constrained the allotrope, the greater the entropy, right? So if we compared carbon to graphite, who do you think is the less constrained allotrope? So think about what happens with respect to graphite when you rub it against your paper. It just sloughs off on your paper, right? Do you think that's very constrained? It just sloughs off? What about diamond? If you rub diamond on your paper, would it leave a mark? No, it would cut your paper probably, but it wouldn't leave a mark, right? So who do you think is less constrained, graphite or diamond? Graphite, right? So graphite, because of that, also will display a higher entropy value because, again, it is the less constrained allotrope. One more little trend. The increasing molecular complexity. Okay, so as we increase molecular complexity, we will also see an increase in entropy. What does molecular complexity mean, though? Overall, with respect to what we need to know, increasing molecular complexity just means increasing numbers of bonds. Okay, the more bonds we have with respect to a molecule, the larger the molecular complexity. So increasing this just means more bonds. So if we took something like carbon monoxide versus ethene, CO and ethene have similar molar masses. So if we utilize the original trend that I showed you, would expect them to have similar standard entropy values, right? But what we find is that ethene has a much higher entropy value. Why do you think that is? What does it have more of comparatively to carbon monoxide? If I drew out the structure, it would look something like this. And then carbon monoxide would look something like this. So what is the difference between these two molecules if the molar mass is the same? Who has the more bonds in it? C2H4, right? Ethene, okay? This guy's got more bonds. We call this more molecular complexity. It's got more places to put energy, okay? And so overall, it is going to have a higher standard entropy value because of that. Okay. So this gets us to my final little point of the night. And I'm going to go ahead, I'm not going to actually finish it. I'm going to let you guys do the activity because we are talking about various aspects of entropy. So remember, the entropy is kind of like a measure of the dispersion of energy into a system, right? It's kind of a measure of the randomness or disorder of a system. So we had talked about our new criteria for spontaneity in the universe. So our new criteria for a spontaneous process tells us that the entropy of the universe must what? Entropy of the universe must increase, right? So this always has to be greater than 0. So this delta S of the universe must be a positive value. So if this delta S of the universe is just the final entropy minus the initial entropy, and this has to be a positive value for this to be a spontaneous process, what does this tell us about the magnitude of the entropy in the final state comparatively to the initial state? Does it have to be larger? Does it have to be smaller? This guy versus this guy. Who's got to be bigger if this is a spontaneous process? We have this positive delta S. Final, right? So what does that tell us overall is that the entropy of the universe tends towards a maximum value. And this is different than the first law of thermodynamics, which tells us that the energy content of the universe is constant. Second law gives us this criteria for spontaneity, tells us the entropy of the universe is tending towards a maximum, okay? So then we talked about how we can look at various types of processes qualitatively and predict the overall entropy change for a variety of different processes, right? So when we go from a solid to a liquid to a gas, what happens to the entropy of these various physical states? Right, so we see this increase in entropy. So anytime we go from a solid to a liquid or a solid to a gas, we can predict that the entropy of that change is going to be a positive value. We'll also get an increase in entropy if we go from 2 moles of gas to 3 moles of gas. Anytime we increase the number of moles of gas, we tend to get an increase in entropy. What were a couple other trends that we saw with respect to entropy increasing? So another trend we looked at was molar mass, right? So what happens to the entropy of something if you increase the overall molar mass of it? We're also going to see an increase in entropy, right? So if we increase the molar mass, we're also going to see a corresponding increase in entropy. What about molecular complexity? We're also going to see an increase in entropy if we increase the molecular complexity of a system. What do I mean by molecular complexity? What did I kind of say that was analogous to bonds, right? So molecules that have bonds have lots of ways to store energy in those bonds. So if we increase those bonds, we increase those ways. We have lots and lots of ways to disperse energy in that system. Entropy, pardon me, and energy. Okay, so that gave us to the point, or that got us to the point where we're looking at these tabulated standard molar entropies. Okay, and so we're going to utilize these tabulated standard molar entropies, which are going to be given in the appendix in the back of your book, to calculate the change in entropy for any reaction that we want to. And we're going to utilize this equation to do that. So this should look fairly familiar comparatively to stuff that we dealt with in 151. So now to calculate this change in entropy for any reaction, all we have to do is we have to sum the standard molar entropies of our products, multiply by their stoichiometric coefficients, and subtract from that the sum of the standard molar entropies of our reactants multiplied by their stoichiometric coefficients. Okay, so note there is a little typo here, and it is this little delta. There is no delta S, it is just S naught. These are what these standard molar entropies represent. Okay, but this delta is correct. Okay, so how are we actually going to utilize these to calculate this standard entropy change, any type of chemical reaction that we can imagine? So let's say that we have this chemical reaction. We have ammonia, and there are 4 of them, reacting with oxygen, going to make NO and H2O. Okay, so how are we going to utilize these standard molar entropies that we have looked up in the back of the book to calculate the overall change in entropy for this reaction? So we'll do that in just 1 second. Before we do that, if we look at this reaction, what would you predict to be the sign of this change in entropy for this reaction? Just looking at the physical states of our reactants and products. So over here, how many moles of gas do we have as a product? We have 10 moles of gas as a product. How many do we have as a reactant? 9. So overall, if we're increasing the number of moles of gas, we would predict this entropy change to be positive. So that could be a good check to make sure that our math is correct. Okay, so let's go ahead and utilize our little equation to calculate this change in entropy for this reaction. Okay, so to do that, I am going to take the sum of my standard molar entropies of my products. First thing I'm going to do is I'm going to look at NO, okay? And I'm going to go ahead and use brackets for this to distinguish. So NO, when I look into the table, has a standard molar entropy of this 210.8, okay? What do I need to multiply it by, though? What is that in the reaction or the equation? Number of moles, right? There's a 4 in front of the NO, so that's what I'm multiplying this by. This is the stoichiometric coefficient. So 4 times this 210.8. Now we should note the units here. So the units for standard molar entropies are joules per mole times Kelvin. Okay? So those are the units that we're putting in here. Okay, so again, we're doing the products first. So that was my first product, NO. Now I'm going to move on to my second product. I've got water. There are 6 of them. So I'm going to take 6 times the standard molar entropy of water in the gaseous form, which is 188.8. And those are my products, right? I'm summing them together. This is why I have this nice little plus in here. Now from that, I am going to be subtracting the exact same thing for my reactants. So for my reactants, I have ammonia. I have 4 of them, so 4 times the standard molar entropy of ammonia, which is 192.8. And again, I'm going to add to that 5 times the standard molar entropy for oxygen, which is 205.2. Okay, so once I have everything plugged in, then it's just about doing math. So for this first bracket, I end up with an 843.2. Now a note again about units. When we take this little n and we multiply it into our units here, the stoichiometric coefficient cancels the moles, okay? So when it comes out of this, the units are going to be just joules per Kelvin. So that's 843 plus a 1132.8. That is the first bracket, and I'm subtracting from that 771.2 plus a 1026. So again, you guys have fancy calculators, you can plug all these in. I deal with my little solar powered calculator. So this is 1976 joules per Kelvin. That is the first bracket, minus 1797. And so when we sum these guys together, we subtract them, take their difference, we end up with a positive 178.8 joules per Kelvin. Delta S naught. Okay, simple, right? You guys did this, we got to it on the activity on Thursday. So just as a quick little note, quick little check, comprehension, what does this little naught mean? What is this little zero up top in the superscript? What is that telling you? Standard state, right? So what does that mean with respect to our reactants and products here? What type of reactants and products, what is the physical state of these guys? They're gases, right? Right? So what does that mean about the concentration, not the concentration, but the partial pressure of these gases that we're dealing with? It's 1 atmosphere, right? This is telling you that the standard molar entropy change for this reaction, when we have 1 atmosphere of NH3, 1 atmosphere of oxygen, 1 atmosphere of NO, and 1 atmosphere of water, is going to be this value that we have just calculated. Okay, so again, that's what that little naught is telling you. Everything is under standard state. Okay, so go ahead and try one. I will look up these values for you so you don't have to go to the appendix. People hate that. They don't like looking in the appendix. I will write them over to the side here. Compound and nope. S naught. Okay, so let's go ahead and talk about this one. Most of you got this correct, I think, if you've logged in. Most people have logged in. Okay, so overall, for this reaction, using the values that I gave you, you should have calculated a change in entropy of a positive 343.2 joules per Kelvin. Okay, so go ahead and plug in these values to show the math specifically on how we got here. So we're going to start with our products. So the products are always on the right side. I'm going to start first with the water. I have 2 times the standard molar entropy of water, which we look up in the table, of 188, plus 4 times the standard molar entropy of SO2, which in the table is 248.2. So done with the products. Now we're going to subtract from that the reactants. We've got H2S, 2 times 205.8. And then for oxygen, we have 3 times O2. O2 is 205.2. So when we multiply these guys out, we add them together, we end up with a 1370.4 minus a 1027.2, which overall gives us a positive 343.2 joules per Kelvin. Great, awesome, cool. Okay, so is everyone good with that? We're going to use this quite a bit in this chapter. So this overall equation, sum of things, etc. We're going to come back to this. Okay, so now this is going to get us into the real purpose of this chapter. Okay, so we have already talked about our criteria for spontaneity, right? Our criteria for a spontaneous process in the universe. What is it? We have a spontaneous process. What must increase in the universe? Entropy, right? So right now, our criteria for spontaneity is that the entropy of the universe must increase, right? So this change in the entropy of the universe must be a positive value, okay? So now, let us consider a certain process. Let's say that we take water, liquid water, okay? So we have H2O as a liquid, and we put it in the freezer, right? What happens to it? Freezes, right? So it takes liquid water, and what do we make? Solid water, right? So below 0 degrees Celsius, liquid water will spontaneously form solid water. If we looked at this process and we predicted the overall, at least sign of the entropy change, what would you predict in taking a liquid and making a solid? Right, so the entropy change of this guy would be negative, right? Because we're ordering the system by taking a liquid and making a solid. So it's important to note right now that this is the entropy of the system, right? This is our chemical reaction, okay? The criteria for spontaneity with respect to the universe, or with respect to everything, is that the universe must have an increase in entropy, okay? But what is the universe? Is it just the system? No. So the universe is not just the system. It is the sum of the change in entropy of the system as well as the change in entropy of the surroundings, right? So right now, for this spontaneous process, this has a negative entropy of the system, okay? We know this is spontaneous though, so this guy overall has to be positive. So if the system has a negative entropy, right, we have a decrease in the disorder, then what's got to kind of overcome that to make this overall a positive value with respect to the universe? So the surroundings, the entropy change with respect to the surroundings have to be, number one, positive, and they also have to be bigger, right? So they have to be bigger than the entropy change with respect to the system. If they are, then when they sum together, we'll still get a positive value, and this will still be a spontaneous process. So now what's going to affect, do you think, the overall entropy change of the surroundings? So what are some various things that we can do, or not really do, but we mentioned that if we increase something or we increase something else, it's going to change the entropy, or it's going to increase the entropy. So let's think about this really quickly. Let's take this back. Let's ignore entropy for a second. And let's consider this reaction in terms of enthalpy. All right, so this reaction up here, our little spontaneous liquid going to a solid, what would be the overall sign for this reaction with respect to enthalpy? Is this an exothermic or an endothermic reaction? Does it release heat or does it absorb it? This releases heat. This is an exothermic reaction, meaning that the enthalpy change here is negative. It releases heat, the system does, to the surroundings, okay? So if the reaction releases heat to the surroundings, what's that going to do to the temperature of the surroundings? So we're going to increase the temperature of the surroundings. And is there any type of relationship between temperature and entropy? Yes, right? What is the relationship? If we increase the temperature of something, what is it going to do to the entropy of it? It's going to increase as well, okay? So if we increase the temperature of the surroundings, that is also going to increase the entropy of the surroundings, okay? So these guys are all tied together. It's not just the entropy of the system that we're looking at. It's also going to take into account the enthalpy of the system, because the enthalpy of the system is going to affect the entropy of the surroundings, okay? Okay, so again, with respect to entropy and this heat exchange, the definition of entropy is a dispersal or randomization of energy, okay? If we release heat to the surroundings, that is dispersing in energy, okay? So that's going to increase the entropy of the surroundings. So anytime we have an exothermic reaction, that is going to increase the entropy of the surroundings. On the other hand, if we have an endothermic process, that means that the system is absorbing heat from the surroundings. It's going to decrease the temperature of the surroundings. It's going to decrease the energy of the surroundings, okay? Or entropy, pardon me. I keep saying the wrong thing. Entropy of the surroundings. So endothermic, decrease in entropy of the surroundings. Exothermic, increase the entropy of the surroundings. Okay, so we can take this even farther. Okay, we can actually quantify the change in entropy of the surroundings given the change in enthalpy of the system. Okay, so we know that the entropy change of the surroundings is going to be directly proportional to the heat released by the system, okay? It's also going to be the negative of that, okay? So we're going to change the sign here because, again, if the heat is released by the system, it's going to be absorbed by the surroundings, which is going to make that positive. We also know that the entropy change with respect to the surroundings is inversely proportional to the temperature. So the smaller the temperature, the lower the temperature, the farther or larger the change in entropy is given an energy exchange, okay? We can combine these two and have our change in entropy with respect to the surroundings equal to the negative heat of the system over temperature. We also know one more thing, that the enthalpy change for a reaction is just the heat of the reaction at constant pressure. Okay, so we can substitute our little Q of the system here for enthalpy of the system, and now we have a means by which we can measure the entropy change with respect to the surroundings given the enthalpy change with respect to the system and the temperature that we're at. Okay, so we're going to utilize this in the following problem. So how would we do? Okay, so let's say that we have a reaction, right, where we know the enthalpy of this reaction, right? It ends up being about minus 2,044 joules. I want you to first calculate the entropy change to the surroundings associated with this reaction at 25 degrees Celsius. Then I want you to determine the sign of the entropy change with respect to the system. This is just asking, is it positive or negative? Then combining these two overall, I want you to tell me whether or not this reaction will be spontaneous at 25 degrees Celsius or not. Okay, so 3 different parts to this. We'll go over it. First, calculate the entropy change of the surroundings. Then positive or negative. Then spontaneous or non-spontaneous. A helpful reaction would be delta S.
Does the temperature have to be in Kelvin?
It sure does. Just 273. Okay, so let's go ahead and talk about this one. So I've given you a means by which you can calculate the entropy change for the surroundings, given the enthalpy change for the system. Okay, so what we'll need is the enthalpy of the reaction, or the enthalpy of the system. When we calculate this, though, we're going to take the negative of that. All right, so I'm going to go ahead and substitute negative times a negative 2,044 joules. This is going to be divided by the temperature. And again, this temperature is in Kelvin. So to convert from Celsius to Kelvin, we're just going to add 273. This ends up being 298 Kelvin. So 298 Kelvin. When we do that, we're going to get a positive value. This ends up being a positive 6.86. And now what are the units here? The units of entropy are joules per Kelvin. Okay, so that's good. We have a positive value here. Now if we look for B, how am I going to determine the sign of the entropy change for the system? I don't need an actual value. I don't need to calculate this. But how would I look at this reaction, our system, and kind of just get an idea of the sign of the enthalpy change, or entropy change? Just the moles of gas, right? So we have 3 plus 4. We have 7 gas moles on our product side. What do we have in our reactants? 6, right? So we have 6 moles of gas as reactants. What do you think the sign of delta S is for the system here? Should be positive, right? And we're just looking at number of moles of gas here. So this is delta S for the system. And we're going to predict that that is going to be a positive value, okay? So now we're going to combine these two to predict whether or not we're going to have a spontaneous process. So as a reminder, the entropy change for the universe is the sum of the entropy change of the system plus the entropy change of the surroundings. So what is my sign for the entropy change of the system? Positive, which we predicted in B. And then what is my sign for the surroundings? Positive value. So what do you think? Is this going to be spontaneous or not? If you add a positive to a positive, will you ever get a negative value? No. All right, so overall, because of this, this is positive. And positive means spontaneous with respect to looking at the entropy of the universe. Okay, all right, so you may have to do that. I don't know. This is going to come in handy in just 1 second. Okay, so next, where are we going to move to? So now we have our entropy of the surroundings in terms of the enthalpy of the system. We're going to utilize that, okay? So as a reminder, our entropy change of the universe is equal to the sum of the entropy change of the system as well as the surroundings. If we want to know whether or not a process is spontaneous, with this equation, we have to be able to measure the surroundings as well as the system, which we usually don't like to do. Okay? So ideally, we would like to take this reaction or take this equation and manipulate it so everything is in terms of the system or our reaction, because we like to just measure one thing and then get every other piece of information from them. Okay? We now have a relationship between the entropy change of the surrounding and the enthalpy change of the system. Right? So we're going to utilize that and we're going to plug it in to our little equation here. Okay? So I've just plugged in this relationship that we derived. So now the next thing I'm going to do is I'm going to multiply both sides by minus t. Okay, so I multiply both sides by minus t. Note here that my t's are going to cancel, and I'm going to be left with a minus t. Entropy change of the universe is equal to the enthalpy of the system minus t times the entropy of the system. Enthalpy of the system and minus t times the entropy change of the system. Okay, so a couple more things. Now, we're going to define a new thermodynamic function. Okay, so this new thermodynamic function is going to be called Gibbs free energy. Okay, and we're going to define Gibbs free energy as the enthalpy minus the temperature times the entropy. Okay, so that means that the change in Gibbs free energy is going to be equal to the change in enthalpy minus T times the change in entropy. Okay, this ideally should start to look something like this, which it does. Okay, so now Gibbs free energy. Okay, Gibbs free energy, delta G, is going to be proportional to minus T times delta S of the universe. So now let's talk about what this means in terms of spontaneity. If we have a spontaneous process, so spontaneous processes, what does that mean in terms of delta S of the universe? What is going to give us a spontaneous process in terms of delta S of the universe? Is it going to be a positive or a negative? Positive, okay? So spontaneous processes in terms of delta S of the universe are positive. What's that going to do to delta G with the negative in front now? So delta G, Gibbs free energy, if I have a spontaneous process, if this guy is positive, I have a minus T in front of it, right? So what is it going to do to delta G in terms of spontaneity? We're going to get a negative, okay? So with respect to delta G, spontaneous processes are going to be negative because there's a negative T in front of the delta S of the universe. Okay, so on the other hand, if we have non-spontaneous processes, delta S, if it's non-spontaneous, is negative, right? What does that mean in terms of delta G then? It's going to be a positive value, okay? So we're kind of switching gears, unfortunately, right? We've been looking at this entropy change of the universe and predicting spontaneity from that. Spontaneous processes with entropy change of the universe have positive values. We're going to switch gears and we're going to say, well, actually, we're going to measure this via delta G, via Gibbs free energy. Spontaneous processes with respect to delta G have negative values overall, okay? Non-spontaneous processes with respect to delta G have positive values overall. Okay, so ideally, this entire thing that we've been trying to do, we have now achieved, right? When we first set out on this quest, we wanted a chemical potential energy, okay? Chemical potential energy, we wanted to be very similar to mechanical potential energy, right? We know in mechanical systems that spontaneous processes tend towards lowest what? Mechanical potential energy, okay? So now, with respect to Gibbs free energy, a spontaneous process is going to tend towards lowest Gibbs free energy, right? Because if we look at this, if we have a delta G that is negative, that means that the G final minus G initial, who has to be bigger? Initial, right? So a spontaneous process, which gives us this negative delta G, the initial Gibbs free energy is always going to be higher than the final Gibbs free energy. So Gibbs free energy is our chemical potential energy. We tend towards lowest Gibbs free energy. Okay, so that's great. We found it. It's here. We now have an equation by which we can calculate it. What do we need to calculate? Well, we need the enthalpy and we need the entropy. Okay, those are the two things that are going to go into determining whether or not something is spontaneous or not. Okay, so this kind of just summarizes. Again, we have our new chemical potential energy. We call it Gibbs free energy. It is proportional to the negative of the change in entropy of the universe. Again, if we have a negative value of delta G, that leads to a spontaneous process. We have a positive value of delta G, that leads to a non-spontaneous process. So let's consider a couple of different scenarios that could lead to various signs with respect to delta G and how they're going to depend on the overall temperature of the system. So now, how are these various things, enthalpy, entropy, and temperature, going to affect the spontaneity of a reaction? So we're going to consider 4 different cases. The first case that we're going to look at is a delta H that is negative and a delta S that is positive. Okay, so delta H that is negative, what is this called? Negative delta H gives us what kind of reaction? This is an exothermic reaction coupled with, what does a positive delta S tell us about the disorder? Not spontaneous anymore, because we're looking just at the system now. Positive delta S, though, means that we are increasing what? Disorder, right? So we have an increase in the entropy, an increase in the disorder of the system. Okay, so now we're going to plug this in to our little delta G equation. So delta G is equal to delta H minus T delta S. And so for this case, we have a negative delta H. So delta H is negative minus T times a positive delta S. So now the question here is, will this ever not be negative? If we have a negative delta H, this is what we call our enthalpic term. And we have a positive delta S, but that positive delta S is coupled with that minus T in front, right? So will this, when we sum these guys together, will they never not be negative? Maybe that's a double negative. Will this never be not spontaneous? How about that? I think that's a double negative too. All right, so we have a negative. When we multiply this negative into this positive, what does that become overall? Negative, right? So a negative plus a negative is going to give us a what? Negative, okay? So when we have an exothermic reaction coupled with a positive delta S, this reaction will always be spontaneous. It does not depend on the temperature. Okay, so case number 2, we're going to do the reverse of this. In case number 2, we're going to have a positive value of delta H. What is this called? This is an endothermic reaction coupled with a negative value of delta S. What would a negative value of delta S indicate about the order with respect to the system? We would be increasing the order. We'd be ordering the system, right? So again, this is going to be a decrease in disorder. So if we plug this guy in, we'll have delta G is equal to a positive value minus T times a negative value, okay? So now we have a positive, and then we multiply this negative into a negative. What does that turn out to be? A positive as well, right? So for this reaction, an endothermic reaction that is coupled with a decrease in disorder, this will always be positive, meaning it will always be non-spontaneous. So this is always non-spontaneous. Okay, so what's the point of this? Who cares, right? So case 1 and 2 are the easy ones, right? It's either going to always be spontaneous or it's going to always be non-spontaneous, okay? Now, there are 2 cases which unfortunately the spontaneity of the reaction is going to depend on the temperature. So this ends up being case 3 and case 4. So in case 3, we have a negative delta H, so we have an exothermic reaction. This is going to be coupled with a negative delta S, so a decrease in the disorder of the system, okay? So when we plug this guy in, we get delta G is equal to a minus T times a minus. Okay, so now how is this going to depend on the temperature? So again, we have our nice little enthalpic term versus our entropic term. And right now they're battling, right? They have this big battle going on, okay? This minus times a minus is going to make this entropic term positive, right? But it's battling this enthalpic term. What is it going to depend on? What is the thing that we can change? The temperature, right? So now, what's going to happen as we increase the temperature? What's going to happen to the magnitude of that positive entropic term? It's going to get bigger, right? So at some point in time, that temperature is going to increase so much that this thing becomes big and more plentiful than the negative from the enthalpy, right? What's going to happen with respect to the spontaneity of the reaction when that entropic thing becomes bigger than enthalpy? It's going to be turned delta G positive, right? And so that's going to be non-spontaneous. So for these reactions, at high temps, we have non-spontaneous reactions. Because again, that entropic term depends on the temperature. When it becomes big, it's going to overwhelm the enthalpic term, leading to a non-spontaneous positive reaction. At low temps, everything is good, enthalpy wins, we are spontaneous. So again, when I kind of pointed this out, I talked about liquid water going to solid water, right? This is a very good example of this type of reaction. When does this occur? Liquid water going to solid water. What temperature do we need to be below? 0, right? So that's a spontaneous process at low temperatures, like below 0. If we go above 0, it becomes non-spontaneous because, again, the entropy wins out. So one more. I'm sorry. I apologize. I know this is terrible. So case number 4 is going to be the opposite of case number 3. So in case number 4, we're going to have a positive value for enthalpy. So we'll have an endothermic reaction. We're also going to couple that with a positive value for enthalpy. Okay, so this is going to be an increase in disorder. So now, when we plug this guy in, we have delta G is equal to a positive minus T times a positive. So again, we still have this battle between enthalpy versus entropy. But now, who's going to win at high temps? They're always going to win at high temps, but who's going to win and make the reaction spontaneous?
Is it the opposite?
It's going to be the opposite, right? Now the entropic term is leading us to this favorable criteria for spontaneity. It's leading us to this negative portion. As we increase temperature, so at high temps, we're going to get that entropic term to dominate, so we're going to get a spontaneous reaction. And then at low temps, the enthalpic term is going to dominate, so we're going to get a non-spontaneous reaction. Okay, so for these two cases, spontaneity depends on temperature, right? You may be asked at some point in time, if we had, let's say, case number 4, for example, at what temperature does this reaction go from being spontaneous to non-spontaneous? So for this one, for case number 4, we have, again, this guy, delta G is equal to delta H minus T delta S. And if I wanted to figure out at what temperature this thing becomes bigger than this thing, how would I do that? If I know delta S and delta H. So what happens here is we have to go through delta G is equal to 0. Okay, and we'll come back to what delta G is equal to 0 in a second, but just note that this is when this reaction is going to switch. It's when delta G equals 0. So at that point in time, we have delta H minus T delta S. I can rearrange this and solve for T. So when I do that, I have T equal to delta H over delta S. So if you have one of these cases where the spontaneity depends on the temperature, and they want you to solve for that temperature, you should utilize this equation. Enthalpy over entropy will give you that temperature. Okay, all right, so that's great. We went over all the cases. So again, this is just kind of like a little summary slide. There's 2 important things to note here. For the cases where the reaction is either always spontaneous or always non-spontaneous, what was kind of characteristic about the signs delta H and delta S versus each other? They were opposite, right? So when we're always spontaneous, always non-spontaneous, we have opposite sides of delta H and delta S. It's only when they had the same sign that the spontaneity of the reaction depended on the temperature, okay? And again, it's going to depend in different ways depending on what their overall sign is. Okay, so let's utilize this in an example. Let's say that we have a reaction, and we want to calculate delta G at 25 degrees and determine whether or not this reaction is spontaneous. So our reaction is given to us up here. We also have the enthalpy value for this reaction, as well as the entropy value for this reaction. So now all I have to do to calculate Gibbs free energy is plug these values into my equation. So delta G is equal to delta H minus T delta S. Now there's only one thing to note here. What are my units with respect to enthalpy? Kilojoules, right? So we have kilojoules up here. What about my units with respect to entropy? joules per Kelvin, right? Can you add a kilojoule to a joule? No. So but someone's got to be converted. For me, for whatever reason, I always take my enthalpy values and I convert them to joules, right? All I have to do is multiply by 1,000. But you could conversely do the same thing by converting the entropy value to kilojoules, by dividing by 1,000. Okay, so now that we're in the same units, all we have to do is plug these guys in. So we have a positive 95,700 joules minus T. The T here has to be in Kelvin. What is 25 degrees Celsius in Kelvin? 298 Kelvin times the entropy value, which is 142.2 joules per Kelvin. Note that the kelvins cancel when we multiply these guys together, and we end up with a value, delta G, is equal to a positive 53,324 joules. Now this should show you really the wrong things that I like to do. Why do I convert it to joules when I just have to take this and I have to reconvert it to kilojoules? I don't know why I do it, but I still do to this day, right? So it's a big number with respect to joules. So if I convert this back to kilojoules, I'm left with 53.3 positive kilojoules. Is this spontaneous or not? Spontaneous reaction. No. What is our criteria for spontaneity with respect to Gibbs free energy? It has to be negative, right? This is a positive value. This is a non-spontaneous reaction. So in part B, they ask us, well, if it's non-spontaneous, at what temperature does this become spontaneous? So for this, I'm going to utilize my new little learned equation, where temperature is equal to delta H over delta S. And I'm going to plug in my values. The only thing to note here is that these guys still have to be in the same units, okay? So as long as they're in the same units, I should get a correct answer. Joules divided by 142.2 joules per Kelvin. When I divide these two, I end up with 673 Kelvin. Usually, unless they're very particular, you can leave it in Kelvin and not have to convert it to Celsius again. Okay, so let's go ahead and try that. I have a reaction. I give you the enthalpy and the entropy of the reaction. And I want you to calculate, number one, Gibbs free energy. I want you to tell me if it's spontaneous or not, and then I want you to tell me at what temperature it becomes spontaneous, I think. Something like that. You'll see when you actually do it. Ran to the ones number. Ones place.
So you gonna want us to round to 1, or do you want just?
No, to the ones place. Are you talking about Kelvin at the end, the third question?
Yeah.
Yeah, so I would run not one number, or not one sig, but to the ones place. So 4 sig.
place for number 1, 2.
I put in 4 sig figs on number 1. It would be the 10th place.
It's not too late for me.
Usually units, if you don't put a space or you don't put the units that I put in. That was, yeah. Okay, so let's go ahead and talk about this. Most of you guys are getting this correct. So all we're doing really is inserting our values. They have to be in the correct units. Okay, so again, I like to convert joules. So when I do that, in my little delta G equation, my enthalpy value becomes minus 137,500 joules. This is going to be minus temperature, which is 298 Kelvin, times the entropy value, which is a minus 120.5 joules per Kelvin. So when we multiply these guys together and then add them, our delta G overall ends up being a minus 101,591 joules. And I'm going to convert that to kilojoules, which ends up being minus 101.6 kilojoules. All right, so is this reaction spontaneous? And how do you know? What is the sign of delta G? Negative, right? So is this reaction spontaneous? Yes. So this is a spontaneous reaction because delta G, which we just calculated, is negative, okay? So for the last one, we're going to do the exact same thing that I just did to calculate this temperature at which this reaction shifts. All I have to do is take my enthalpy value in joules. So this is minus 137,500 divided by my entropy, minus 120.5 joules per Kelvin. And when I do that, it's getting bad, it's time to end it. We end up with a 1,141 Kelvin. So now, the question is, this reaction at 25 degrees Celsius is spontaneous. What happens at 100, or what happens at 1141 Kelvin? Does it turn from being spontaneous to non-spontaneous, or is it spontaneous below that temperature, non-spontaneous above? So above 1,141 Kelvin, is the reaction spontaneous or non-spontaneous? It's non-spontaneous, okay? So this is, again, one of these ones where we switch depending on the temperature. For this one, when we have a negative delta H, negative delta S, we're going to become non-spontaneous at these high temps. We're going to be spontaneous below that. One thing to note, okay? This only applies to things where we have the same sign for delta H and delta S. What if we were dealing with a reaction that had opposite signs? So it was either always spontaneous or always non-spontaneous. What's going to happen when we try to solve for a temperature like that? If we have delta H, let's say negative, delta S positive. We're going to get a negative temperature. Do negative kelvins exist? No. It is the absolute scale. The lowest it can go is 0. There's no such thing as negative kelvins. So if you ever get a negative kelvin doing something, you may want to think about whether or not this would ever be either spontaneous or non-spontaneous.